In this video, we want to explore how to actually use the concept of the electric field to calculate the electric field at a specific point given a small collection of individual point charges. So, for example, let's say that we have two charges and the origin is here. And even though they look somewhat symmetric, let's make them off balance from the origin. And let's say that we'll call this Q1, we'll call this Q2, and we'll say that this distance is 1 centimeter from the origin, and we'll say that this distance is, let's say, 3 centimeters. Let's say 2 centimeters. And let's let Q1 have a charge of 1 coulomb, and let's let Q2 have a charge of negative 2 coulombs. Okay, so we'll say that Q1 is positive and Q2 is negative. Okay, and the question now is, let's say, what is E? Let's say it this way. What is the electric field at the origin? So if I put a point right at the origin in between these two charges, we'll call this point P, right? Point P. At point P, what is the electric field due to this collection of point charges? Okay, and charges, it turns out, individual point charges follow what's called the rule of superposition. Okay, and the rule of superposition simply says that the total electric field, or the net electric field, if you will, is just equal to the sum of the individual fields, right? So whatever the field from charge 1 at point P is, plus the field from charge 2 at point P, all I have to do is then add those together, and that will give me the net field. Now, I have to be very careful here, pardon me, because these are vectors, so I have to take the sign into account. And let's come back here and let's officially define our axis, all right, and we'll define to the right to be in the plus direction, and we'll implicitly assume that this is in the plus x direction. Okay, so with that being said, we know that, let's look at Q1 here. Q1 is going to have its electric field lines emanate like this, right? So along the axis, the field lines will be pointing away from the charge, and they'll get smaller in magnitude as I move away from the charge. Likewise, if I look at Q2, which is negative, the field lines are going to be pointing toward the charge. So the field lines along the axis are going to look something like this. Okay. So what does this have to do with our particular situation? So let's come back and redraw our situation here. Here's the origin, here's Q1, and since we say that Q2 is a bit further out, let's put Q2 way out here. Right, so there's Q2. So here's my positive charge, here's my negative charge, this is 1 coulomb, and this is negative 2 coulombs. Okay, so what are the field lines going to look like here? So they're going to look something like this, right? And they'll get weaker as we go out. And so what this means is, when I'm evaluating the electric field at my point P here, when I'm evaluating the electric field at point P, the electric field due to Q1 is going to be in the positive x direction. So the field is going to get a positive direction. So when you looked at the formulas for Coulomb's law in the electric field, you notice that the charges themselves in the laws or in the formulas get absolute value signs. So the formula only tells you the magnitude, but then it's up to you to decide the direction, okay? And that's going to be based on the charges. And so in the region between the two charges, of course, the field lines due to Q2 are also going to be in the positive direction, and they're going to die off the further out we go. And they're also closer to the charge. They're going to be twice as big as the field lines emanating from Q1. So with that in mind, what we can see is that my net external, or my net electric field, will have a positive X value. So the field will be positive. Okay, the field will be positive. And that's due to the fact that both charges in the vicinity of P are pointed in the plus X direction. Okay, once again, we've defined this to be in the plus X direction. So, for example, let's say that Q2 was actually positive. Since the field lines emanate away from the positive charge, the field lines in between the two charges would actually be opposing each other, and it would depend on if the magnitude was larger due to one of the charges as to whether or not the field would be 0 or if it would have some value. All right, so now let's actually do the calculation. So we know that the electric field is given by Coulomb's constant, the absolute value of the charge, and we'll call this E1, divided by R1 squared, right? And E2 is also going to be given by Coulomb's constant, the absolute value of charge 2. It's not a very good 2. Let's see if we can make that a little bit better. And then divided by R2 squared. Okay? Now, at this point, I'm going to just leave the calculation like this. All right. And what that symbol at the very end, what this plus X hat means, is that this is just going to be in the positive X direction. Okay. You can carry out that calculation. Now, of course, you're going to want to convert this into meters. Okay, you're going to want to convert your centimeters into meters, so it should be 0.01 meters squared and 0.02 meters squared. Okay, and you can plug in the value for K, which is, of course, 9 times 10 to the 9th. Newtons times meters squared per coulomb squared. And your overall answer should give you newtons per coulomb. All right, and that's the value of the field. Now, there's one final point that I want to make here. Okay, there's one final point that I want to make. Now, you can carry out that calculation, and that is a general way to do things. Okay, and it does not matter how many charges you have. All you have to do is look at the individual charge, find the direction the field is pointing from that charge at the point you're evaluating, and then calculate the field due to that charge, and then repeat that procedure for each individual charge. So, for example, if we had a slightly more exotic example, and I'm not going to carry this out to its extent, its fullest extent, but suppose we had something a little more exotic, where, again, I'm going to put my point P at the origin. That's where I want to evaluate the field at. And now I'm going to put 3 charges on here. And so we'll call this Q1, Q2, and Q3. All right. And let's make both Q1 and Q3 positive. Oop. And we'll make Q2 negative. Okay. So if I want to draw the field lines from 1, and I'm not going to worry about the magnitudes, okay, but the point is, if I want to draw the field lines from 1, the field lines from 1 are going to look like this, right? They're going to be emanating away from the charge. The field lines from 2 are going to be pointing toward the charge. And again, the field lines from 3 are going to be pointing away from the charge. So if you define, once again, this to be in the plus x direction, okay, if you define right to be in the plus x direction, if I'm evaluating the field at point P, let's say I know this distance, we'll call it R1. We'll call this distance R2. And we'll call this distance R3. So when I'm evaluating the field from Q1, when I'm evaluating E1, E1 will be positive. E2, however, at point P, E2 is pointed in the negative direction. So E2 should get a negative sign. Okay, E2 will get a negative sign, as will E3, because E3 is also pointed in the negative direction here. Okay, so you will want to be sure to take those signs into account as you are performing your calculations. Okay. So when you go back into the superposition principle here, you will want to make sure to assign your pluses and minuses appropriately. All right, so just be sure to do that. And the way you do that is to actually draw the direction the field lines are going to be pointing due to those individual charges. All right, so that's how you define the sign for each individual charge and then add those up. And this holds for as many charges as you want to put. As long as they're on a straight line, this method will work. Right. In the next video, we'll talk about what happens if my charges aren't all along the same line. What if some of them are offset? All right, then we'll have to use some trigonometry. But for the moment, this is how you evaluate the fields due to charges along a straight line. We'll see you next time.